Here is a combined summary of the 2 pages. Data streams present unique challenges in machine learning, particularly when it comes to data normalization. The authors of this paper investigate the effects of normalization policies and distance functions on classification accuracy in data streams. They argue that experimental protocols that assume a fully normalized stream can lead to unrealistic and biased results. The authors evaluate 8 well-known distance functions: Euclidean, Manhattan, Chebyshev, Minkowski, cosine, Mahalanobis, standardized Euclidean, and Canberra under different stream scenarios. They compare the accuracy of these distance functions with and without normalization, as well as with normalization, considering the statistics of the first batch of data received and the previous batch received. Their results show that using the original data stream without normalization, combined with the Canberra distance function, can provide more realistic and better results. The authors also find that distances such as cosine and standardized Euclidean can be more sensitive to feature changes over time than Manhattan and Canberra distances. The paper highlights the importance of considering the normalization policy and distance function when dealing with data streams. The authors emphasize that unrealistic assumptions about the stream, such as knowing the minimum and maximum values of each feature in advance, can lead to poor results. The authors employ the min-max normalization strategy, which is simple to compute and understand. However, they note that this approach is sensitive to outliers, as it deals with minimum and maximum values. The paper also defines and explains the 8 distance functions used in the experiments, including their equations and characteristics. The authors discuss related work on data streams, including the importance of considering the serial dependence of the data and the need for adaptive normalization techniques. They highlight the limitations of current approaches and the need for more realistic experimental protocols. The research paper discusses the impact of different normalization policies and distance functions on the performance of a KNN classifier in data streams. The authors propose a novel approach, focusing on the effects of various normalization techniques and distance functions on the classifier's accuracy. They use a synthetic dataset, C-concepts, to test the performance under different scenarios, including varying feature ranges and different normalization policies. The results indicate that the choice of normalization technique significantly influences the accuracy of the classifier, with the Canberra distance showing promising results in some scenarios. The study also highlights the importance of considering the previous batch for normalization, as it often leads to better performance. Additionally, the paper includes experiments using real-world datasets, such as airlines and gas sensor, to further validate the findings. Overall, the research emphasizes the need for careful consideration of normalization policies and distance functions in data stream applications to achieve optimal performance. The research paper discusses the impact of different distance metrics on the accuracy of a classifier in various datasets. It presents a comprehensive analysis of Euclidean, Manhattan, Chebyshev, Mahalanobis, standardized Euclidean, Minkowski, and Canberra distances. The authors demonstrate that the Canberra distance is the most resilient, leading to good results in various scenarios. They also highlight the importance of avoiding full dataset normalization, as it can lead to biased results. Instead, using the original data or normalizing with the previous batch can be beneficial. The study concludes by recommending the Canberra distance as a default metric for stream scenarios due to its simplicity and effectiveness. Here is a combined summary of pages 7 and 8 of the research paper. This study investigates the impact of 8 distance functions and 3 normalization approaches on data streams. The authors test these approaches using 1 synthetic and 5 real-world datasets, revealing that the normalization policy significantly influences the classifier's competence in data streams. They suggest using the original data without normalization, as it yields the best results in 3 out of 5 tests. Moreover, the authors demonstrate that different distance functions lead to varying results, with the Canberra distance function showing the best performance in most tests. The study also highlights the limitations of this work, including the lack of consideration for scenarios where feature ranges change frequently and the overhead of updating normalization over time. Future works aim to test other scaling techniques, such as the z-score, and explore other classifiers and classification techniques that depend on distance metrics. The authors provide a comprehensive review of related works, citing numerous studies on concept drift, data normalization, and distance metrics. They reference papers on adaptive normalization, leakage in data mining, and comprehensive surveys on distance, similarity measures between probability density functions. The study's findings have significant implications for real-world applications, such as concept drift adaptation techniques in distributed environments for real-world data streams. The author's suggestions for using the original data without normalization and the Canberra distance function can be applied to various domains, including electricity, gas sensor, and cover-type datasets. In conclusion, this study provides a thorough analysis of the impact of distance functions and normalization approaches on data streams, offering insights into the best practices for dealing with concept drift and normalization in real-world applications.